you know, it should be quite easy. So now that you're familiar with all those notations, right? So our goal is to minimize, remember, the loss function LW. So we want to find the W star that is the minimum, hopefully like a global minimum of that loss function, okay? So what we're looking for is a W that minimizes our loss, and we call it also the optimal solution to our problem. So we're optimizing, this is an optimization problem, okay? So what we need to do is first compute the gradient, right, and solve these n equations. Why we have n equations? Because now, from now on, we're going to talk about n-dimensional space. So you're solving, you know, the derivative with respect to each direction, and all those derivatives, they should be equal to 0. So you're solving a set of n equations. Now, let's look at this case. So I would like you to take a minute and think about a strategy, okay, an algorithm on how to find the minimum of this function. So you know that what we can look for, we have two things that we can use in calculus, first derivative and second derivative, or gradient and Hessian, okay? So given these two tools, can you think of an algorithm or a strategy on how to move along this curve, okay, to find the optimum W that will minimize our loss L of W? So I'll give you just, 1 minute and try to think about an idea and write it down. Okay? Think about a mini algorithm, like something small, like, or maybe a hint. Think about something that might lead you to developing an algorithm that will enable you to find your optimum, which in this case, right here. But we don't know, because here we can visualize, we can plot the function, but generally we cannot see it. We don't know its shape. We don't know its ups and downs, right? It's a high dimensional complex function. We have access to its gradient. We can also compute its Hessian matrix at different points, okay? But then we don't know how to move, how to find the optimum. So think about that. Okay, but this case, this simple case, should give you a hint. We always start with simple. Remember, we go from particular to the universal. Lecture 1, right? Think about also the initial and ending conditions of your algorithm. When should it stop? When does your algorithm know that it found the minimum? Okay? Okay, so any ideas? Yes?
First, we can compute the gradients.
Okay, we compute the gradient.
Then check this Hessian's matrix.
Okay, so
See
we are on a maximum, or whether, but we might not be like, remember the Hessian matrix or the second derivative, it just tells you whether your point is minimum and maximum or a saddle point. So you need you need to be there already.
yeah. So then we put this in a recursive fashion.
Okay,
And then
you're repeating the steps. So what are you repeating exactly? How are you moving?
in this step, I will this, update this coefficient that I have already found.
Mm-hmm.
This function. And as I counted these W's, I updated each and every iteration.
Right, so you're going in a good direction. So you talked about, updating the W's, computing the gradient, maybe integrating Hessian matrix. Okay, so for now, let's keep it simple. Let's think about slopes, okay? But there is something there is still missing. We're going to find it.
And the missing part is this moving speed.
The moving speed, yes, speed or momentum. There are many, so that's one thing we're gonna look at in the next lecture. But for now, yeah, so these are good words you're throwing, but it needs to be, there's a story that's kind of missing a little bit. You know, how are you moving from, one point, like let's say W0 to the next one? How do you know where how you're moving? Sorry, yeah, go ahead. It's okay.
I start
Randomly.
randomly.
So randomly is good, but sometimes imagine randomly might be good, but imagine that your function has many local minima. So it's like very complex topology. Like you can't even know where the valley is, where the hills are, where the lakes are. It's like, your ground is like completely it's not very smooth. It depends, right? It might be smooth, but you might have many local minima. Okay, it goes up and down. So if you start randomly, it's good. Randomization might help, but then you need to learn how to move locally when you randomly select your point. Okay, so you're saying many good ideas, but yeah, like futuristic more. Okay, yeah.
Actually, it's not. It is included in gradient matrix.
Right.
Take a random point
Okay,
and calculate the gradient around this point.
which is a slope. Okay.
And move along the direction that has the greatest descent.
Okay, so you probably have an idea. Do you have an idea about the gradient descent strategy? A bit, but it's a good hint. So basically, you're following the slope, right? So you're going downward. So you want, when you're starting at a point, you're computing the gradient, and then you're looking for the next point that minimizes, basically, that makes the your slope makes you go downward, not upward. You're not climbing, okay? You're just walking downward. Yeah, good.
But
Yes?
maybe many points, many directions that leads to the decrease in the.
But the gradient gives you a good direction.
Yes.
The gradient is the slope, so it gives you, a good direction in all dimensions, because remember, the gradient is along all directions, right? It's a vector. So it tells you how to move. In one-dimensional space, it's just one line, so it tells you need to go downward. Let's look at this, guys. So here, if I start at W0 and I compute the gradient, so what do we have here? The gradient, is it a negative or a positive slope? Negative slope, okay? So a negative slope, if I do omega 0, let's say, for example, I write something like this, okay? Evaluated at this point, will I go in this direction towards the right direction where the loss is decreasing, or will I go in the other direction? So remember, this is negative, right? So if I subtract something negative, I'll be moving in the wrong direction. So what I need to do, I need to go in the opposite direction of the gradient. Okay, so that's how I know that I'm moving. So this is a negative slope. I'm moving in the right direction. So the easiest way is, let's say I compute the gradient, then I move, you know, maybe using a fixed length, right? I don't know, let's call it alpha. And then I reach this point, okay? So then after moving, when I reach that point, probably it's like, let me just put it in a better way. So a tangent maybe like this, okay? So here I move at length from here to there, it's alpha, okay? Along the opposite direction of my gradient, okay? And I found myself where? Right here. So I just, you know, project this, and this is my second point, okay? So I'm minimizing my loss. And then what I do, I hop back onto my loss. So I take this point, so I compute L of W1, okay? And then compute the gradient again. Maybe something like this, okay? Take the same step alpha. I find this point right here. Project it, okay? Then I know I can basically compute again the L of W2. So I hop back onto the function and compute the gradient again. So I'm computing the now L prime at my second point, okay? So that is my gradient. Now I'm computing L prime at W2. And I do it again. So I have I stop right here, so like my alpha. I project, so I have like my measurement, etc. So you guys get the idea. So this is, you know, what we call the gradient descent. Why it's a descent? Because we're going downward always, okay, constantly, and we're going in the opposite. We're using the gradient to know in which direction we're moving, okay? So this algorithm is, you know, algorithm number 1 in optimization, and we call it gradient descent, and the simplest one. How do we know when to stop? What is the stopping criteria for this algorithm? How do we know that we reach the minimum? Yes, so when the gradient or the first derivative becomes close to 0, when it's very small. So you know when you're computing numerical optimization, you will not get 0, right? You'll get 0.000 something. So you need to constrain your gradient at your optimum point that we're looking for to be something smaller than epsilon, okay? Like a very small number. So epsilon can be something like this, okay? Yes?
How do we know we're not at a local minimum?
Very good question. Very good question. Okay, so here,
I also have one more question.
yeah.
Why can't we use the first derivative, set it equal to 0, and find all the critical points, and you know how we did in calculus?
That is good, but generally, computing basically you're starting from you want to compute the derivative and find, sometimes it's not easily solvable, you're gonna see. So, you know, the easiest way is to compute a local approximation, but you cannot numerically calculate the derivative or the Hessian, like numerically derive it. So locally you can linearly approximate it. Why? Because a linear approximation is easy, right? It's rise over run. It's not difficult. A linear approximation of a function can be easily obtained than trying to derive the whole mathematical formula of the function, because you might not have access to that at all. Okay, so that's question number 1. Question number 2, how do we know that we reach a global minimum, not a local minimum? So if you guys look at this function, it's not convex, right? Because it has different minima. So it's a non-convex function. So this is what I asked right here. So this is a non-convex function, right? And how do we know that we are, so right here, you can see in this case, we found a good optimum. But if we start off right there, our W0 start off right there, we're going to follow the slope too, right? We're following the slope. And we're going to end up having finding, WK right here, which is a local minimum. So this does not really solve our problem well. So it's problematic, okay? So happily and luckily, in most of many machine learning problems, the function to optimize turns out to be convex, okay? But so in a convex function like this, it's wherever we start off at, okay? We're going to always go down and found the minimum because it's convex, even if we start right here. Okay, so convex functions are how do I say, are the joy of a machine learner. Okay, so this is the algorithm. Let's summarize it. So the basic idea is start the minimization process from some initial point W0. So you're just fixing your parameter. Like say I'm gonna start right there. So that's, you fix your values for your vector. Then you take iterative steps. Going downhill by following the negative of the gradient of your function, right? And you're going to repeat this. So you're going to loop over it, as I explained earlier. And the stopping condition is this. So there are two possible stopping conditions. So the first one is you just, stop after a pre-specified number of iterations are completed. So you say, I'm going to just reiterate 1,000 times and then just stop, okay? The second one is you stop when the gradient is small enough, which means it's smaller than an epsilon, right? And it's very small. So the first one is problematic because you might not, depending on, we're going to see, depending on your step, the length of your step, the step you're taking, you might spend your lifetime trying to go to your minimum, but you never reach it, okay? So, so fixing the number of iterations is not a good strategy. So the second one is the best one, okay, for now. Now, let's look at this. So this is just a summary of what we call the gradient descent algorithm to optimize a loss function for our machine learning problem. So in what we're looking for is we're starting first at an initial point, W0. We travel in the downward direction of a linear approximation, which we can hopefully compute, okay? And then we found we approximated and then go down this direction. Then we hop back onto the function because we're computing, again, the gradient at, W1. And then repeat again. So we're going to loop over until we know that we have reached our minimum where the gradient has a very small value, close to 0. That's it. So, right. So, think this is, let's look at the formulation of this. How do you write it down? So basically, this is the linear, if you guys remember. This is the first order linear approximation of our loss function, okay? We're starting off at a fixed point, W0, and then we're going to compute the next point, W1. How do we find the next point? It's equal to our first, initialization minus some step, like the length of the step we're taking in the downward direction, multiplied by basically in the direction of the gradient. It's the negative of alpha and the gradient. This is how we calculate this, so you should know this by now. And here, what you guys notice, we have different steps. In the example I've given you, I used exactly the same step length, okay? So alpha 1 is equal to, alpha 2 is equal to alpha 3. Generally, we tend to fix the step at each iteration, but we can change that. We can learn that, okay? But for now, let's say we fix the step alpha. Right, so this is actually the formula of your gradient descent, and this is how we find our optimal final W star after many iterations when the gradient becomes close to 0. Okay? Right. So now let's look at this example. So we have, so this summarizes everything. So this is what we call the steep descent direction minus gradient of L of the first initial point W0. And right, so to see if you guys understand this, let's look. Let's say we're taking this as our initial point. Then we need to move, if we compute the slope, right, the gradient. Is it positive or negative? In this case, it's positive, right? But to go down, we need to go not in the positive direction because our slope is positive, but we need to go in the negative direction. So we take minus, okay? And then we move by a small step alpha. So minus alpha gradient of L of 0. And we start at this one. And then we're going to get, this is exactly our point right here. Okay, you got that? It's quite simple. Great. Then you guys know how to do it this way, so we've done it already. So we're moving downward in that direction. Now, how to choose the alpha? This is quite problematic because let's look at this first case. Okay? I'll give you a second. Look at this. What's the problem with this case? If we select or choose a very large alpha, so the length of our jump, okay, is so big. So in the first one, we're going to go from our W0, move downward. This is our alpha. And right here, compute the gradient again. And what we'll find, if we take the same alpha, same length, right, then we'll find this. We overshoot the minimum, right? So the minimum is right there. So this is not good. A quite large alpha is not good. Now, if you look at this one, okay, the second case, we have a small alpha. So you can see it's very small, like the length we're taking for our steps are quite small. So you might spend a long time to reach the minimum. So that's not really good. So here the alpha is something, it's quite a problematic parameter, but generally what you can do, you can test a few values here and there. So it's like how you fix it. Let's say for today, you can learn it, but how you fix it without learning is empirically try a few values and see how your function, your loss function changes. If you can see that the change is very, very minimal, then you know that your step is too small, right? So you just, kind of try to empirically tune your parameter alpha. Great, so let's summarize. So this is the gradient descent algorithm. So for what we call a differentiable function L, differentiable means we can derive it many times, okay? And this is the condition that holds from the beginning of this lecture because we're computing partial derivatives and derivatives. So we hypothesize, I suppose, that our function, loss function L is differentiable. And we have a fixed step length alpha and an initial point W0. So what we're going to do, we will repeat until stopping condition, and stopping condition is like when the gradient, so you guys know the stopping condition is when the gradient of the last WK is smaller than an epsilon. Great. Now I'm going to give you a demo. So this is, from the book Machine Learning Refined of Jeremy Watts and colleagues. And they have, I will send you the GitHub link so you can have access to all chapters. And also you can have access to all codes in MATLAB, Python 2, and Python 3. So there is an implementation of the convex gradient descent algorithm. So I think, guys, it would be very nice if you can look at this. Okay? You read the code in Python, you run it. And I think in Python, I'm not sure, in MATLAB it's complete, so you just run it right away. But I think in Python some parts might be missing because they have incomplete code, so you can just try to fill in what's missing and run those, understand them, play with them, and this is how you will learn. Okay, great. So let's run this demo.